Team Kestava, what's going on? Rich back here again, another example for you. And now that most of you or some of you have wrapped up your PE exam, it's Saturday here for me, so those taking the SE exam, they just wrapped up their second day. If you did back-to-back with the lateral and then with the gravity and then the lateral, congrats to everybody making it. Hope you did well. Let me know. Send me an email, contact me, leave a comment, however you wish, and because I want to know how you did. Today we are jumping into another design example, so we're kind of pushing away from those PE example, study prep, tabbing, all those types of videos getting you ready for the PE exam, and we're going to bring it right back into our core design videos. So today we are going to get back to shear wall design. That was a really, really highly recommended one that a lot of you wanted to know more about. So we're doing wood construction again, and we are going to finish wrapping up how to design a shear wall. So before we did kind of those three, we checked the global stability of our shear wall, and now we're really going to get down into the nitty-gritty of, well, how do you size the thickness of sheathing that goes on there, the structural panels, what type of grade, where do you get that information? We're talking about hold downs. How do you size hold downs? What are even hold downs? Where do you get that information? And then, nailing patterns, all that kind of stuff. How do you transfer loads through a shear wall down into the foundation? That's all going to be explained here, and I'm going to show you a step-by-step example on how to size all of that, the calculations involved. So let's giddy up. As you can see here, we have a shear wall design example, and I actually used this from our previous example, thumbnail above, with the global stability, but I've repurposed it and changed it a little bit. So how we're going to start off today is a single shear wall, and it's 20 feet long by 10 feet tall, as denoted. You have a 1 foot thick by 2 foot wide concrete stem wall running below, continuous. We have a roof dead load of 25 PLF, which is pretty light. And then we have kind of the wall dead load, so the self-weight of the wall at 50 PLF. And we have a force FE that I've denoted over here. What is that? So that's where we're going to start. So FE, that is going to be, and I've wrote it above here, lateral loads for this problem is lateral loads induced by seismic criteria. So not wind, this is going to be seismic. So FE, I've just kind of made it up. It's not really what you call it out as, but once you go through all the steps to find your force, which again, we'll do some problems on that later. But right now I'm going to start you off with a force that's being applied. But I'm not giving you a point load at the shear wall. I'm going to take it one step back a little bit, and I'm going to give you a distributed load along the diaphragm. Let's assume there's a wood diaphragm. This is a flexible diaphragm, and FE is the distributed load from lateral forces due to seismic. So FE is going to equal 150 PLF. And for a flexible diaphragm, that means it's all just tributary width for distribution of forces. It doesn't have anything to do with stiffness criteria of the shear wall. It's just purely tributary width. So I am going to say, so if we go here, here, we need that dimension. And I'm going to say that is 30 feet. So that's the amount of tributary width of lateral forces that are going to be transferred to this shear wall. And that just means that now that would give us a point load, which we will call big E, as denoted, and it would just be simply 150 PLF times your trib of 30 feet. That's going to get you 4.5 kips. So now you have, I'll draw it in green for you, now you have that big point load that's going in to our shear wall. And we are going to design per the NDS manual. This is wood construction, so we want to stay in ASD design criteria. And first we're going to find how to size the appropriate sheathing or structural panels for our shear wall. So that's the first step. So with that, we definitely want to stay in ASD because in the NDS, they give you capacity criteria depending on the type of sheathing that you choose and nailing pattern that you choose, and it's all in allowable capacity. So we want to match those. We don't want to mix them up or else it's going to get really confusing. So ASD when you're sizing your sheathing. And we want the worst case criteria, obviously, per ASCE 716 criteria. I'm not going to pull up the ASCE 716 today for us, but I will be pulling up the other codes as we move along here, give you step by step. But really, we're just going into chapter 2, I believe, of the ASCE 716, which is just load combinations, obviously. And we need to flip over a couple pages in and talk about load cases that involve seismic. And now within those, I will give you a little brief summary here. You'll see two sections, one for LRFD and one for ASD. And then you'll see two broken down groups of load cases, one with omega and one without omega. So those are overstrength factors, is our omega. I can't recall if we've talked about this before, but I may be going a little fast for you. But basically, omega, we don't need the load cases with omega in them for this type of design. So just go with the ones without omega, and the one that's going to control 0.6 dead. I'm already messing it up. 0.6 dead minus 0.7 EV plus 0.7 EH. Well, dead load for this case, because it's just purely shear, we don't need to consider dead load at the moment. We just need to look at our lateral forces, or pure shear that's being transferred through that sheathing. So we just really want to check out, and same with EH, because this is your seismic forces, EV. That's your seismic forces in the vertical direction, so up and down. The forces acting on their structure, moving it up and down due to seismic event, is EV. So we don't have to worry about that either. That's for overturning, foundation design, stuff like that, bearing pressures. So don't worry about anything like that. So we just need EH, which is horizontal effects due to seismic loading. And EH is really just going to equal the 4.5 kips, but we just need to reduce it now. So 0.7 times 4.5 kips. That's going to get us 3.15 kips. And now what's really happening here is you have your shear wall, you have EH, but that's not really representative of how the forces are going to transfer through the shear wall. They're not all going to be lumped as a mass loading at the edge of the wall. It's really going to be distributed along the length of your shear wall, as I've shown here. So we need to break that up, which is going to be, and again, I've called that 20, our shear wall is 20 feet long. So we need to take that 3.15 kips, divide it by 20 feet, and break it into a line load, because when we go into the NDS, you're going to see that all of your capacities for your shear walls, shear wall plywoods and structural panels are broken down in line load criteria, capacities. So 3.15 divided by 20 is 158 PLF. All right, now that's assuming that this whole wall right here is just totally solid. There's no penetrations in it, there's no doors, windows, anything. You need to be careful, because actually, we'll just use the same one as an example. If there was a big door here, let's say that door is 5 feet wide, then you'd have to look and say, the shear is traveling across and through that shear wall, which means that up top, with my dashed line here, you have the entire length of sheathing, and you have sheathing all across the length of that wall, so you can distribute it all the way across that 20 feet. But you need to check for the worst location along your shear wall. And if you see my second dotted line here, this guy here, you see that the length of sheathing that we have to transfer that lateral forces is now only 15 feet worth of shear wall, because we have the 5-foot penetration. So that would be 0.7 times 4.5 kips, which gets you 3.15 kips, divided by only 15 feet. That then would mean that you have 210 PLF as your required shear forces that need to transfer through your shear wall. So you need to be careful of that. But in this case, we are just going to assume that we have no penetrations. So we're going to get rid of this. but I wanted to make everyone clear of that you could have a window here, you guys see what I'm talking about here, and that's more indicative to real life design. So even though you have up above here, you have full shear wall, really, everything good. In terms of shear, you got to go down, it's got to travel all the way down that wall down to the foundation. So right there, just for sheer capacity only, you would be screwed along those windows and doors. So you'd have to really check that out. And that actually dives in, I'm getting off the rails here. That actually dives into what's called perforated shear wall design. So you start to get into, let's draw it in green because it's getting too crazy. Is that actually a little shear wall? And is that actually a little shear wall? Same with this one out here, and this one out here. Are these now 4 little tiny shear walls? So it breaks down to a couple different ways that you can start to analyze your shear wall or shear walls, and then you get into drag strut designs and stuff like that, and all mishmash kind of stuff like that. So it can start to get a little complex, but we need to know the basics first, right? So we want to start with just plain shear wall. So I'm just going to leave it all there. No, I'm not. Let's get rid of all this. Get it out. Okay, we're back. Just our full non-penetrated shear wall. It's a thing of beauty. Okay, so we have VREC, not V ultimate because we're in ASD, of 158 PLF. Now we need to check out the NDS, and actually we need the special provisions for wind and seismic design code for the NDS, and that's a whole separate book. It's really thin, but that's all your lateral design for wood design. So let's jump over to that. So here we are, SDPWS. This is the 2015 edition. They have the 2018 out now, so I still just wanted to run through the 2015, but they're almost identical. Maybe I'll do a video eventually to show the differences as we bump up to the new code, but just roll with me on the 2015. All right, here we go. So we need to go to shear wall or structural panels, and let's head there now. Fuck, how do you rotate this? So here we are, table 4.3a, so nominal unit shear capacities for wood frame shear walls. This is wood-based panels, so that's what we want. There's a few others, so if we go down to the next page, it looks identical, only they say wood structural panels applied over 1/2" or 5/8 gypsum wallboard or gypsum sheathing board, so that's a little different. But we don't have that. We just have the sheathings going right up against the studs, being nailed directly to the studs. And don't be confused when you look in here. I'm going to scroll up for you. Let's see if I can find it. So 4.2C, so this is nominal unit shear capacities for wood-framed diaphragms. So diaphragm, again, that's our lateral element. It's kind of our flat lateral element. That's the floor, basically, that's transferring forces to our shear walls. So they have the same setup and still table 4 point something, but don't get confused with that. That's not what you want. We want shear walls. So let's go back down. All right, so here we are. And if we look here, we are going to look through and we're going to say, well, we want wood structural panel sheathing. It's going to be this guy here. That's pretty typical. And then let's go with I'm down with going with a 5/16. We'll bump it up a little bit. We'll do a 7/16, which means that here's minimum fastener penetration in framing members or blocking. So that's just typical there. That's for your specifications of how the contractor needs to build this in order to get the required or the desired design capacity of your shear wall. So all of this stuff you would specify in your drawings. 8D nail is the type of fastener that you need. And then you have 2 criteria. You have seismic, which is A, and then you have wind, which is B. So we're under seismic loading design, so we're obviously in A. And then you go down to edge panel fastener spacing. So this is all of the nailing along the edges of each individual board of plywood, and the plywood or the sheathing is usually 4x8. And then, so all that perimeter nailing, that is your edge fastener spacing. You have nominal or typical fastener nailing, which is different. That's like the inside portion to your studs, and there's a couple other criteria. So, but panel edge fastener nailing, that's the most important criteria because that's how shear mainly gets transferred through each of these panels, because they get transferred through the nails into the sheathing and then back down and then transferred out through the nail again into the next nail of the panel below, and so on and so on. So it really breaks all the way down to that flow of forces. And then you see here, so spacing, you have 6-inch spacing, 4-inch spacing, 3-inch, 2-inch. So we're going to say 4-inch spacing, and then you have CVS here, and there's your units, PLF, so pounds per lineal foot. That's why we were talking about getting it into PLF before. Now, we have, 158 PLF as our required shear. And so if we scroll down here, we don't need to worry about G sub A right now. We just need V sub S. V sub S in our category is going to fall into right here. So that's 700. Okay, so 7/16 is overkill. So let's actually back it out. And let's say, let's say 3/8. See, this is all it is. It's trial and error here. This is how it works. So 3/8. Let's go 3/8. And slightly different fastening criteria. You can get away with a 60 nail. Penetration can be a little less. And then we're going to do 4-inch still. Or, you know, we can do 6-inch spacing now. And let's go with, we said 3/8, so right there. Boom. V sub S is going to be 400 PLF. So let's go ahead and jump back. So phi VS going to equal 400 PLF. So we have V sub S is 400 PLF, and you might think, oh, plenty, we're done. Well, let's take a look back because you need to check this out. We're not quite there yet because you don't have your factors there. So phi or omega, what's going on with those. So let's go check that out. So if we go back to the NDS, you'll see here, look at footnote here. You always want to read the footnotes for these tables, and there's usually a lot for wood. Number 1 is nominal unit shear capacity shall be adjusted in accordance with 4.3.3 to determine ASD allowable unit shear capacity and LRFD factored unit resistance. Whew, tongue-tied tonight. So let's go jump over to 4.3.3 and check that out. So here we are, 4.3.3 unit shear capacities. If you read the top here, basically it boils down to, if you're doing ASD, that in the capacities in that table, you need to reduce them by a factor of 2 for ASD, and for LRFD, you need to reduce them by multiply them by 0.8. So that means, let's jump back, that our 400 PLF is actually going to be phi Vn over omega equals 400 divided by omega, which equals 2.0, which is just going to equal 200 PLF. Now this is not omega for overstrength. This is just omega, like omega for ASD, where you have phi for LRFD. So don't confuse those, okay? So 200 PLF. Well, now we're all done, and that is still greater than V required, which is equal to 158 PLF. Boom. So we're okay. So you would specify, just one more time if we look back, a 3/8 inch thick wood structural panel with 60 nail fasteners, and panel edge nailing would be 6 inches on center. So that would be the type of criteria that you would be specifying for your shear wall design. Hey everyone, so that was part 1 of 3 of how to design a wood shear wall. So I realized after doing all of the recordings that I have a crazy amount of footage. But that was part 1 of 3. We're going to get into the next video an anchor bolt design, and then the third part is going to be the hold down design. So again, a lot of info, so thanks for hanging in. As always, like and subscribe if you haven't already.
tell everyone you know about this channel, because we're blowing up. So that's all. I'll see you next time. Later.